Thank you for the reminder on recording, Martin. Um, so a lot of you put on a post, but not a lot of you responded to other posts. So do make sure you're doing both of those things for the full credit on those forums. This week, I'm going to go back in a little bit and adjust the scores for this first one because it is our first week and we're getting used to all this stuff. So I don't want that to, us trying to learn all this stuff. We're all trying to get used to all of this. So I don't want that to hurt anybody too much. But in the future, make sure you're doing both of those things, giving a post and giving a reply. Ideally, as we do this more and more and you guys use those more and more, it'll just become the habit. You'll be getting more out of it. You'll be posting more questions. You'll be discussing things with each other more, and making sure you have enough stuff there won't be an issue because that's just where you'll be spending some time. But to kind of get used to that, I do want you guys to have the pressure of needing to give at least one post and at least one reply. Let's see. I did also want to again encourage you guys. I've been talking to some of my other classes today, and I do want to encourage you guys to turn those cameras on. A couple of the students in some of the other classes were talking about how much it helped them to have other people's cameras on, help them express themselves better, and they could kind of see how everybody was doing. It helps me see how you guys are doing, helps us form more of that community. I certainly do understand if you're like, no, I'm not comfortable with that. You might be in an FBI witness protection program or something. That's probably the best reason. Other than that, it just might be I don't know, you're looking disheveled. Don't worry about looking disheveled. No one's going to judge you here, except maybe Sam. So he's a little, anyway. But so don't worry about that. Sometimes if you got a lot of people who are going to be moving around in the background, or there's a lot of other things going on, it can be certainly a little distracting. So if you're wanting to avoid that, that's totally reasonable. But do what you can. In addition to that, I do want to make sure you guys recognize that under your chat menu, if you're having trouble bringing up that chat menu, don't know where that is, watch the videos or let me know, and I can help you find it. But there should be in your big menu thing that has chats. I think on yours, because you have less commands on yours than I do on mine, I think that chat is just in your list of commands. So do make sure that's open so we can talk. At the bottom of that, near where you type in your chats and where it says to everyone, there should be a little box with 3 dots for more. Under that, there are some extra commands, so you can use that to give a thumbs up if you just want to say, yep, that makes sense. So I know you guys are doing okay. If you open your manage participants, you guys can't do a lot to manage the participants because you're running it, but you can still bring that up, and that allows you to kind of see everybody that's here. And on the bottom of that, I added a bunch of nonverbal interactions you guys can use. So you can use those to express yes, no, go slower, speed up. You can even thumbs up, thumbs down. You can even applaud with it. Yay, if you want to, yay. You could, I'm on a coffee break. So you can use those to give different ways of communicating if you're not comfortable. And of course, again, also you guys are muted when you come in, so it's not too noisy, but you can turn that mic off and say something, or sometimes turning the mic off is a lot of clicks. For most of you, you should be able to just hit your space bar. That'll unmute it while you're having that space bar down. Say what you want to say, release the space bar, you go back on mute. So I do want you guys trying to communicate as much as you can. I know I've said that before. I'll probably say it again. But I've been getting more feedback from the students who are doing those things, to asking me to try to get more people to do it, because it is helping them, one, feel like they're in a more natural class environment, and two, it's helping them get a little bit more out of it when that happens more. So you're not just helping me, you're helping, you know, Nick and Martin and Felix and Samuel, and helping everybody. Okay, that's that's the gripes. So other than all of that, is there anything that you guys want to ask about or look at before we start talking about our standard angles today? Everybody good? Got a couple nods. A couple people found the thumbs up button. That's great. I can, of course, start using long, awkward pauses to try to put some pressure on people. But let's talk about those standard angles. Let's see. We know what those standard angles are from some of our other work. So we looked at, you know, we can take these axes that are 0 or 90 degrees, or our pi over 2 radians, our pi radians, and our 3 pi over 2 radians. We cut those in half to make the pi over 4s. We cut those into thirds to make our pi over 6 and our pi over 3 angles. Did the same thing down here, here, and here. One of the things I told you guys I really wanted to encourage you to do is practice filling out the radian measures in these. We do want to build up that intuition. So having getting yourself some paper, some pencils, some pens, a straight edge can help. And going through and labeling these radian measures can really can help work towards giving you a good feel for radians. Those of you who are going on to any kind of engineering or physics or, you know, many applications, you'll start using radians more and more often. Those of you going into electronics, even kind of the like mechatronics work, they actually often use radians quite a bit. People are often quite surprised. We don't hear or see a lot of radians in our casual kind of conversation life, but as soon as you start doing anything fairly technical, they come up and they don't go away. So getting good with them, getting comfortable with them is important. So just to kind of go through this construction again, it's probably the last time you'll see me go through it. I'm gonna again encourage you guys to practice it, but you know, if we're starting our measure from our standard position, our positive x-axis, we remember that all the way around is 2 pi radians. So about 6 1/4, 6.28 radians to get all the way around. Half of that would be pi radians. So it's a little more than 3 radians to get halfway around. Half of that's going to give us pi over 2 radians, about 1.57 radians to get halfway around. It's equivalent to 90 degrees. If that's pi over 2, that's 2 pi over 2. This is going to be 3 pi over 2. So it's 1/2 of pi, 2 halves of pi, 3 halves of pi, and then 4 halves of pi. Cut that pi over 2 in half, and we'll get pi over 4. And then, as we've done before, we can count those pi over 4s all the way around. So 1 pi over 4, 2 pi over 4, which would reduce 3 pi over 4, 4 pi over 4, which is pi, 5 pi over 4, 6 pi over 4, which would reduce 7 pi over 4, and 8 pi over 4, which again would reduce. So that's our pi over 4s. Those are our 45 degrees, essentially. And then for our other ones, instead of cutting this in half, this actually looks a little bit more like halfway than it should. But instead of cutting it in half to get pi over 4 and then in half again to get pi over 8, I wanted to cut this into thirds. So a third of pi over 2 would be pi over 6. So that's 1 pi over 6. That would be 2 pi over 6s. I'm going to write 2 pi over 6. And then 3 pi over 6, which would reduce. 4 pi over 6. 5 pi over 6. 6 pi over 6, which would reduce. 7 pi over 6. 8 pi over 6. We'll reduce that in a second. 9 pi over 6, which would reduce to 3 pi over 2. 10 pi over 6. 11 pi over 6. And then 12 pi over 6, which again reduces to 2 pi. We then might as well take a moment, and these 2 pi over 6s, I do encourage you guys when you're counting to count all the pi over 6s, but we could certainly reduce that to pi over 3 instead. 2 pi over 3, and you really should in the long run. 2 pi over 3. I'm going to erase those. So pi over 3, 2 pi over 3. That's going to turn into 4 pi over 3 and 5 pi over 3. Now we could do the pi over 3s by counting pi over 3s as well. That would be 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3. I tend to recommend counting the pi over 6s instead. The only problem with counting the pi over 3s is oftentimes people will go 1 pi over 3 and they want this 90 degrees, this y-axis, to be 2 pi over 3s. And then they get 3 pi over 3, 4 pi over 3, and their count is off. So the thirds do skip over the half. So oftentimes it's just easier to count the 6s. But however you want to count your way around those, getting used to this idea of counting is really handy because we want to be able to build this thing kind of in our heads as well as on paper, because we want to, again, start thinking this way. So if somebody then comes up to us later and asks us, where is, I don't know, 17 pi over 3, they might ask us what quadrant that's in. So if we just want the quadrant, we can answer that. Somebody might ask us to find something that is coterminal to it. And we want to be able to handle those questions. So 17 pi over 3, well, 17 pi over 3 is certainly more than one rotation, but where exactly is that going to land? This idea of counting can be really helpful. We can just count pi over 3s until we get to 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pi over 3. 13, 14, 15, 16, 17 pi over 3. So 17 pi over 3, 17 pi over 3 would land down here. So 17 pi over 3 is in what quadrant? It's in quadrant 4. 17 pi over 3 is coterminal. Well, it's coterminal to a lot of things. In the first rotation, it's coterminal to 5 pi over 3. So the better sense we have of how this is built, the easier it is for us to start, manipulating things this way and thinking this way. But even if it was something bad, let's say we had negative 42 pi over, it doesn't even have to be one of these nice angles. Let's say 42 pi over, I hate to do that, but 7. Even thinking in pi over 7 is horrible. This is a lot of backwards rotations. So we'd be going back this way. We could recut this thing into sevenths if we wanted to, but I really don't want to. But if we wanted to figure out what is this coterminal to, we can just start adding and subtracting rotations to this. Because I don't know where this is, but wherever it is, it's coterminal to anything we get if we add or subtract full rotations. The difference between 17 pi over 3 and 5 pi over 3 is a full rotation. The difference between them is what? 12 pi over 3? And 12 pi over 3 is the same as 4 pi. So that's different by 2 full rotation, 2 versions of 2 pi. So if we add or subtract a full rotation to this, we will get something that's coterminal to it. So if we take negative 42 pi over 7 and say we want to make it positive, so we add a full rotation to pi, we will get something else that's coterminal to this. Essentially like adding or subtracting 360 degrees to an angle. Now, to do that, we would need common denominators, so I don't actually want to use 2 pi. How many sevenths are in 2 pi? A weird question. How many sevenths are in 2 pi? Good, 14. So that would turn into 14 pi over 7. Now we're talking about one rotation in terms of sevenths. If it was pi over fifths, well, then 10 pi over fifths is a full rotation. 12 pi over 6 was a full rotation. 6 pi over 3, 8 pi over 4. It's just got to reduce to 2 pi. But then if we add those together, we get what, 28 pi over 7? It would be negative, but negative 28 pi over 7. So negative 42 pi over 7 and negative 28 pi over 7 are coterminal. Now, if we wanted something that was positive and in the first rotation, we'd have to add another 2 pi and keep adding 2 pi's until we get to something nice and positive in the first rotation. So in general, when we talk about trying to find an angle that is coterminal to an angle theta, to find that, we're going to take whatever that angle theta is, and really we're going to add any multiple, any k multiple of 2 pi if we're in radians, where that k is any integer. Remember, integers are positive or negative whole numbers, so we don't need the add or subtract because that k can be negative because it can be an integer. So any multiple of 2 pi, add it or subtract it, and we'll get something coterminal. So instead of adding 14 pi over 7, we could have added 28 pi over 7. We could have added any multiple of it. So, or we could add another one onto this, plus another 14 pi over 7 would be negative 14 pi over 7. Add another 14 pi over 7. We just keep doing this. Hey, we get 0 pi over 7s, or 0. Hey, so negative 42 pi over 7 is coterminal to 0. And of course it is, because you could have reduced that to negative 6 pi. So that's negative 2 pi, negative 4 pi, negative 6 pi. So doing this construction, not only is it good practice for dealing with your radians, but it's a good practice for visualizing why we do a lot of the other tools or why we do a lot of the other procedures that we do. because it helps us add meaning to those processes. Questions about any of that? I know fighting with coterminals can take a little while when you're working in radians. It's not because coterminals is so complicated. It's just because thinking in radians, learning to think in radians takes some time. But you really do want to make sure you put that time in. Every once in a while, you get some folks who are like, I don't like radians. I'm going to stick with degrees. Trust me, later on, you're going to start hating degrees because they cause a lot of trouble because we can't use our nice tools on them. So we do want to get to the point that we're comfortable with that. And that takes kind of embracing them and letting them suck for a while and finding your peace with it. But what I want to talk about for the most of the rest of the day today is why these particular angles are the angles we care the most about. Taking this, wanting the angles for 90 degrees and 180 degrees and 270, wanting those should seem reasonable. Even taking that pi over 2 and having it to get pi over 4. But like, why do we care about pi over 6, but we don't care about pi over 8? Why the third and not the fourth of it? Why do we care about pi over 4 and pi over 6 and pi over 3, but not pi over 5? Why are these the ones that are important? And that's the big question I want to answer today. And the short answer to that question, the reason why those are the ones we care about, is because those are the angles that inside a triangle give us access to some very nice little geometric tricks that will allow us to figure out what these lengths are geometrically. So just from knowing the angles, knowing the geometry, we won't need to use anything else. We won't need to use some table or a calculator or some other weird mechanic to figure out what the lengths are. We can use straight geometry. And I'll show you how we do that. So let's say this is these are right triangles, ideally. So, I might have drawn them a little off, but they look rightish. If this angle is, say, our 45-degree angle, 45 is the degree version of our standard pi over 4. So I'm just going to label that pi over 4. But if it helps to remind yourself that's a 45-degree, great. If that's a 45-degree angle, we can actually find the ratio of all of these lengths just by geometry. Because if this angle is 45 degrees, then this angle has to be 45 degrees because they have to add up to 180. If this is pi over 4 radians, equivalently, this has to be pi over 4 radians because, again, those angles have to match. Fair? Our 90, 45, 45, they all add up to 180, or our pi over 2, pi over 4, pi over 4. If we added those together, we'd still have pi radians. They'd still add to the equivalent of 180 degrees. Are we all comfortable with that idea, by the way? It is not trivial that all the angles in a triangle always have to add up to 180 degrees. But there is a nice way to kind of prove that if you want. There is a formal proof to it, of course. But if you want to just kind of do a kind of a fun proof, it actually is exactly how the formal proof is done. But at some point today, grab a piece of paper, draw with nice straight lines, draw a triangle, any triangle you want, as crazy as you can make it. And then take some scissors, cut it out, and cut out the 3 corners. No matter how crazy you drew that triangle, as long as it's got straight lines, if you line up those 3 corners that you cut out, you will always end up with them lining up on a straight line. It's impossible not to. So it can be a nice exercise. Take a triangle, and I encourage you guys to do these things. They really do help us think through things. Brings that visual learning, that kinesthetic or hepatic learning. So encourage you guys to do these things. Draw a little triangle, cut off the corners, and you'll see they always, if you line them up, will add up to straight, no matter how crazy it is. So with this pi over 4 angle, we know this angle also has to be pi over 4, which means that these two sides, I'm going to call this side A, this length A. If this length is length A, then this length has to be the same length. These two sides have to be the same length because they are created by the same angles. It's an isosceles right triangle. Remember, isosceles means two of the side lengths are the same. So these two sides are equal. That's going to be helpful. If we want to find the ratio between the sides, we could actually label this other side anything we want. Just to be nice on us, I'm going to label this side just as a 1 unit of length. But if it was 10 or 20 or 87 or whatever it was, we could set up an equation between these three side lengths and try to solve it for A. Because our trig functions talk about ratios, all we really want is the ratio of our sides. So letting this be any number and then finding what these other two values are is going to allow us to set up those ratios. So how do we determine that? How do we, express the relationship between this one and those two side lengths? Well, as we talked about yesterday, good old Pythagorean theorem. We know the sum of the squares of the two sides has to equal the square of the hypotenuse. But the fact that those two sides, those two legs, are both the same is going to allow us to do more in this problem than we normally could. Then we let that C be the 1 squared. You can imagine if these angles were different, that would be an A and a B. These sides would be different, and we'd be stuck with A squared plus B squared equals 1. And you can't solve that. But because these are both A's, because of that pi over 4 angle, we can keep going and solve this. Throw in our square root, and we get a nice A equals, plus or minus the, square root of 1 is 1 over square root of 2, which we would, of course, rationalize to the square root of 2 over 2. Now, as I've said before, we do want this plus or minus. For right now, since we're talking about a triangle, we'll use the positive one. But this geometrically allowed us to determine that not only is this side length the square root of 2 over 2, but this side length is the square root of 2 over 2. So we geometrically know all the side lengths in that triangle up to some ratio. So now if somebody came along and asked, hey, buddy, what is the sine of pi over 4? Or according to our definition, the sine of an angle should be the opposite length over the hypotenuse. You'll see why I wanted to make this a 1. So the sine of pi over 4 is that opposite side, the square root of 2 over 2, divided by the hypotenuse, 1. Divided by 1 means just throw it out. So the sine of pi over 4 is the square root of 2 over 2. Exactly. So why pi over 4 is one of our standard angles is because we're able to determine the trig functions for that angle based strictly on geometry. If somebody asked, hey, what's the cosine of pi over 4? Well, cosine of pi over 4 would be the adjacent over the hypotenuse. Hey, it's still square root of 2 over 2. It's not common for those to equal, but it should seem reasonable that because this pi over 4 is this kind of perfect symmetry, it should seem reasonable that, you know, the ratios for this pi over 4 are going to be the same as the ratios for that pi over 4. There's going to be a lot of symmetry going on. Even the tangent of pi over 4. Take a moment and write in the chat what you get when you try to take the tangent of pi over 4. Felix, yeah, absolutely. We get a nice one. We get the opposite over the adjacent. You guys are all working to have those memorized. It takes a little while to have those memorized. But the tangent is the opposite over the adjacent. So square root of 2 over 2 divided by square root of 2 over 2 is indeed 1. We could do the cosecant, secant, and cotangent by taking these reciprocals. So strictly based on geometry, we can determine all of our trigonometric values for pi over 4. That's very unusual. Most radian angles, it's very difficult, or most radian angles, most angles in degrees or in radians. Most angles, it's very difficult to find the trigonometric values. That's why we have the calculator do it for us. But there are a couple angles where we can do geometry things like this to get at their values. And it might seem obvious now, but the angles where that's possible are pi over 6, pi over 4, and pi over 3. That's why there are standard angles. So this triangle, the pi over 4, 90 triangle, or if you prefer in degrees, the 45, 45, 90 triangle, degree triangle, is one of those standard triangles and a really good thing to get down. So doing this build a couple of times, drawing this out a couple of times to try to get down, so you can have it with you when you need it, these relationships is going to be super handy for us. Questions about that particular triangle before we look at the next one? Jay, no, you guys good with that? Other than those three, are you guys good with that? Keegan, sounds good. All right. Cool. So the other triangle here is actually really nice because if this is, say this looks a little bit more like the big angle. So if this is our pi over 3 angle, that's the big 60-degree equivalent. I do want to encourage us not to think in degrees and force ourselves to think in radians, but we need to bridge it a bit. So if this is our pi over 3 angle, our 60-degree angle, then this other angle is going to be its complement, the other 30 degrees. So it's going to be pi over 6. So this triangle is going to give us both the pi over 3 ratios and the pi over 6 ratios all in the same triangle. So we'll know the stuff for pi over 6 and the stuff for pi over 3 just from knowing this one triangle. Now the troubling part is even if we make this side length 1 like we did before, we still have this side length A and this side length B that we don't know and need to figure out. So we could certainly say that A squared plus B squared is equal to 1. And we could solve for both A and B, but they'd be in terms of each other. We'd have, A equals something in terms of B, B equals something in terms of A. it doesn't, just going to the Pythagorean theorem here doesn't allow us to know what A and B are as strict values when this is a 1. So we're going to have to do something a little bit fancier than we did with the um, up there. A little bit fancier than we did with the 45-45, the pi over 4 triangle, because we don't have the nice symmetry. But it isn't not a complicated, it's a nice little trick. If we take this triangle and flip it over on itself, to make this one big triangle, then this pi over 3 angle flips over to here, making this pi over 3. This pi over 6 angle flips here, making this pi over 6. But pi over 6 plus pi over 6, or 30 degrees and 30 degrees, 30 degrees plus 30 degrees is 60 degrees. So pi over 6 plus pi over 6 is pi over 3. All three of these angles match. If all three of those angles match, then correspondingly, each one of these sides match. This reflection forms an equilateral triangle. So if that length is 1, it flipped here to make this length 1. But most importantly, this bottom length, because all those angles are the same, this bottom length is also 1. From there to there. If that bottom length is 1, then this short length that we called A a second ago, this short length must be half of that 1, so that short length is 1/2. Again, this is all in ratio, so we did choose this 1 arbitrarily, but whatever this length is, this short length has to be half of that. So if this was 5, that would be 2.5. If this was 10, it would be 5. If this was 84, this would be 42. Fair? We still want to know this other side length, that B value. But now that we have these two, we have enough information to robustly use Pythagorean theorem. So 1/2 squared plus B squared equals 1 squared. And we can take that and solve for B. And that will give us the third side, and we will know, again, up proportions, we'll know the 3 sides of our triangle. So take a moment, solve this for B, and write over in the chat what you got for that B. I'll give you a minute or two to do that. So write in the chat what you get when you solve that for B. Felix, 1/4, not quite. Yeah, no, wait. Check that a little bit. B squared is 0.75, true, but we want to solve that all the way for B, and we really don't want to go into decimals because the square root of 0.75 is an ugly thing to work with. So, Shay, oh, Shay, you didn't even fall into the trap because you remembered the plus or minus, right? All right. So 1/4 when we square the 1/2 plus B squared equals 1. So subtract the 1/4. So B squared equals 3/4. That's your B squared equals 0.75, but we're not going to go to the decimal. And then, yeah, as you guys are doing, square root both sides of that. B equals plus or minus, because we square root both sides. That square root of 3 is just going to stay square root of 3. But as you guys are doing, that square root of 4 is 2. Didn't even need that much space. So this B length here is a nice square root of 3 over 2. And the fun thing to do is then carefully get rid of all of this other stuff, all the purple stuff, and then people go, how did you find that? And we don't tell them the secret because we don't want other people to know. Or you dedicate your life to teaching it to other people. Those are your choices, really. So again, if somebody comes along and asks us, what is the sine of pi over 6? We can use this triangle to tell that. If somebody asks us what the cosine of pi over 6 is, we can use this triangle to tell that. Even the tangent of, say, pi over 3, we can answer with that triangle. The sine of pi over 3. So we got a couple minutes left here. Take a little bit and determine what each of those are. Heck, for the fun of it, I'm going to throw back in a cosine of pi over 4. Pi over 4. So take a minute. That's 1, 2, 3, 4, 5. Take a minute and find the ratio values for those 5 trigonometric questions. And I'll give you a minute to do that. You don't have to type them in the thing. Just find them on your paper and we'll go through them. So at first, this is going to take, a bit because we're trying to remember what each of these ratios are. We're trying to get used to these um, um, triangles. Frankly, at this stage, for like your first test, for example, even just a question like, what is the sine of pi over 3 is a perfectly reasonable test question at first. But by the time we get into week 4, week 5, we'll have done moving around this thing, working with these and other triangles, and worked with these trig functions so much that these questions become kind of automatic. By the time we get to the final, you'll be spouting these things off the top of your head like they're nothing. And you'll look back at that first test and go, how did I get those wrong? Well, that's because right now there's a tremendous amount of information we're trying to get used to all at once. And I want you to keep that in mind. This first chapter, chapter 6, is a tremendous amount of new things being looked at in kind of a new way that doesn't tend to make a lot of sense until it all makes sense. It has to kind of all click together before you start being able to think in the way you need to be able to think to do this stuff nicely. So let yourself be kind of okay with that. If you're struggling with putting all the little pieces together as we keep adding pieces, be okay with that. That's natural here. You're looking for that moment when it all kind of clicks together and starts to look like one big whole instead. And once you get to that stage, it all becomes a lot easier, and we can play with it and have a lot more fun. But at first, it's a little bit of an overwhelming amount of information all at the same time. Be okay with that. That's natural. You know, you've gone through years and years of algebra where you were always kind of, talking about the same basic tools, adding little tricks and techniques to them, but it was always more or less the same conversation. One of the things Math 112 does is all of a sudden we're talking about new weird things that if you've never been introduced to before can just be a little bit daunting all at once. Allow that process to happen, right? Don't be too hard on yourselves about it. And certainly don't panic. But if we want the sine of pi over 6, go to the pi over 6 angle. Sine should be opposite over hypotenuse, so 1/2 over 1. It's a nice 1/2. You can see why I like the 1 here, right? All the divided by hypotenuses. Your book goes through the same basic construction, but it makes the hypotenuse lengths a 2 instead, which avoids as many fractions, frankly, but it's just troublesome later. So there's many reasons why I like to use a 1 instead, and I'd like you guys to kind of try to follow that, even though it does make a little bit more fraction work happen. It really will make our day easier by the time we're done. And not just because of the hypotenuse, dividing by hypotenuse thing. So the cosine of pi over 6. So again, we're at this pi over 6 angle. Let me grab a color here. We're at this pi over 6 angle. So, but because we're cosine, we want its adjacent over hypotenuse. So square root of 3 over 2 over 1. Again, not going to write the over 1. Tangent's always a little bit worse. Tangent of pi over 3. So we're going to go to the pi over 3 angle. And we want its opposite over adjacent. So opposite square root of 3 over 2 over the adjacent 1/2. The halves will cancel. You can multiply by the reciprocal if you want. Get 2 over 1 and cancel the 2's out. Either way, that'll reduce to the square root of 3. Heck, the better thing to do would be multiply top and bottom by 2. Turns into a square root of 3 over 1. But either way, we end up with nice square root of 3. Sine of pi over 3. Again, we're going to go to the pi over 3. But this time we're doing sine. So for this pi over 3, we need opposite over hypotenuse. So opposite, square root of 3 over 2 over 1. Notice, of course, it is the same as the cosine of pi over 6. You should remember that from our cofunction identity. The sine of an angle is equal to the cosine of its complement. That's what the cos mean. So the fact that these two things are equal should be perfectly natural. Cool. Lastly, cosine of pi over 4. We got to go to pi over 4. Oh, pi over 4 isn't here. Pi over 4 is over here. So technically we could grab either one, but I'm going to grab this one. So pi over 4, cosine wants the adjacent and the hypotenuse. So that's again back to the square root of 2 over 2 over 1, or square root of 2 over 2. So hopefully you can imagine that with practice and getting these triangles and these angles and these trig functions, getting those relationships down, which takes time, but once you have those down, you can bust these angles out and these ratios out super quick. Or you can not get the practice in, not put that time in, and have these relationships bog you down through everything else we do. Trust me when I tell you, the first one of those things is easier. Put that time in now, get to practice with these relationships. Even if you're like, oh, now this makes sense, perfect, I'm fine. Spend that time. The better you can be at this, the faster you can be with these relationships, the easier everything else is going to be. And not just here, but in calculus, in physics, in engineering. People whose trig is a little bit soft, you end up suffering for it forever. So don't let that happen to you now. Okay. Any questions about any of this stuff? I'll let you go play with this. We'll start talking about our other definitions of the trig functions, because you probably notice, here we're talking just in these triangles. But over here, we've got all these other angles, right? One of our next big jobs is to take these triangular definitions for these trig functions that only make sense in triangles and extend those definitions to any angle, even angles that could never live in triangles. So we're going to take these ratios, these triangles, these values, and extend them into our circular definition as we go around this thing. So that's what we're going to start doing tomorrow. Bring questions. If there's anything you guys need, send me a message, send me an email, send a pigeon, whatever it takes, let me know. And until I see you tomorrow, have a wonderful day. Bye. You're welcome, Samuel. Sam. I'm going to start calling you Samiel in front of it. Dominic, how about you? You doing good? Anything you need? Well, if it does come up with something, let me know.